So in this video, I'm going to solve the linear system above by the method of augmented matrices. The method of augmented matrices is just the greatest way to solve a linear system. Quickly, it involves taking the linear system, right, original linear system, all right, original linear system, and then mapping it to an augmented matrix, okay, with the coefficients and the constants on the right hand side, then using row operations to reduce that augmented matrix to reduced row echelon form. So we have reduced row echelon form of the augmented matrix. Then going back to what I call the land of equations to write a new linear system, okay, new linear system that is equivalent to the original linear system insofar as the solutions to the new linear system are the same. And the good thing about the new linear system is that it can be solved by inspection. So that's kind of the strategy. All right, so the first step is to take the linear system and create an augmented matrix. So there's the augmented matrix corresponding to the linear system, on the left. Okay, so let's apply row operations to reduce this linear system to reduced row echelon form. All right, so what are the row operations that are that can legitimately be employed to produce an equivalent linear system? Well, the first thing that we can do is we can interchange any two rows. That's equivalent to interchanging any two equations. There's no harm done to the solution there. Multiplying any row by a non-zero constant. Again, that's like multiplying an equation by a non-zero constant. Doesn't affect the solution. And the operation that I like the best is to add a multiple of one equation, one row to another. Or, we could subtract a multiple of one equation from another. That also produces an equivalent linear system. So without further ado, let's get started. Given the fact that I have a leading 1 in the upper left-hand corner, I'm going to use that leading 1 to wipe out the numbers in the column of that leading 1. This will, begin our journey to reduce row echelon form. Okay, so the first row stays intact, right? And then what I'm going to do to turn this 4 into a 0 is take 4 row 1s and subtract it from row 2. So row 2 minus 4 row 1s. So 4 minus 4 1s is 0, as desired. 5 minus 4 2s is negative 3, right? Because 5 minus 4 2s is 5 minus 8. 6 minus 4 3s is negative 6, because 4 3s is 12. So 6 minus 12 is negative 6. And same here, okay? We obtain a negative 6. All right, good. The next step is to take 7 row 1s and subtract it from row 3. So 7 minus 7 1s is 0, again as desired. 8 minus 7 2s is 8 minus 14, that produces negative 6. And 9 minus 7 1s is 9 minus 21, and 9 minus 21 is negative 12, right? 9 minus minus 21 is negative 12. And the same thing over here, we have negative 12. Okay, well, you can see that row 3 is a multiple of row 2. And that's going to be a convenient thing, because we'll be able to turn the numbers into row 3 into zeros. First, I suppose, let's multiply row 2 by negative 1/3. In other words, divide by 3. So what do we get when we do that? Well, I'll write a new one. So good. So let's do that. So we have 1, 2, 3. 3, and then divide row 3 by 3, so we have 0, 1 by negative 3, 2, 2. Good? Good. And then if we divide row 3 by -6, which is the same as multiplying it by -1/6, so we don't, violate the row operation, we have 1, we have 2, and 2, right? So now all we have to do is subtract row 2 from row 3. So row 3 minus row 2. I'll do that right here, okay? So 0, 0, 0. Good. All right. So this is step 1, this is step 2, step 3. Okay, let's see where we're at now. Well, in order to, so we're going to take our leading 1 here to proceed to reduce for echelon form. We'll take this new leading 1 and use it to turn this 2 into a 0. How do we do that? We take row 1 minus 2 row 2s. All right, so I'll go down here for step 4. All right, so what do we have? We have row 2 stays intact, 0, 1, 2, 2. Zeros in the bottom row, and then we have row 1 minus 2 row 2s. Well, 1 minus 2 zeros stays a 1, and that's a good thing. And then we have 2 minus 2 1s, that's a 0. 3 minus 2 2s is -1, and so thus we get a -1 here. Well, look, folks, in step 4, we've achieved our stated goal. We've reduced a matrix and reduced an augmented matrix and reduced row echelon form. You see we have a leading 1 here, zeros elsewhere. The next leading 1 staircases down, zeros elsewhere. And the third row does not have a leading 1. So that's fine. This is reduced row echelon form. Okay. So we're completed with the second part of the algorithm, right? The first part of the algorithm, turning the linear system into an augmented matrix. The next part, reducing that augmented matrix to reduce row echelon form. So I'll erase the intervening matrices and just keep the last one. And then we're going to go back to the land of equations, as I said before. -1, -1, okay. What do we have here? 0, 1, 2, 2, and then we have zeros. All right. So going back to the land of equations, let's see how we do this. Well, we have much easier linear system, right? That I claim can be solved by inspection. We're pretty, close to it. We have x minus z equals -1. We have y plus 2z, okay, equals 2. And then we have nothing having to do with anything else. So we have a linear system, a new linear system, which is much smaller. Well, working from the bottom up, we see that there's no requirement for z. Thus, z is a free variable. So it's customary to let z be equal to t. Well, if z is equal to t, then y is going to be equal to 2 minus 2z, therefore y is equal to 2 minus 2t. And finally, x, right? What is x equal to? -1 on the right-hand side, add z to both sides, so we have x is equal to 1 plus t. Thus, our solution to this linear system, S, is equal to the set of all coordinates in three-dimensional space, such that x is -1 plus t, right? And then we have y is 2 minus 2t, and then we have z is equal to t, such that t is any real number. So that's the solution. All right? Good. How about we check the solution? So to check the solution, we substitute the values that we get. Now this here, if you've taken Calc 3, you'll see that this is a line in three-dimensional space. In parametric form, we can write that line as x is equal to -1 plus t, y is equal to 2 minus 2t, and z is equal to 0 plus t, if we want to write it like that. And so we can put a parentheses around that, say such t is any real number, or t goes from -infinity to +infinity. So the solution is a line. There's infinitely many solutions. This is different from the linear systems that I solved in a previous video, for which the solution was unique. This solution is not unique. infinitely many, and they all lie on this line here. This line can be drawn by starting at the point -1, 2, 0, and then going along a vector v, which is equal to 1, -2, 1, infinitely many far in both directions. Okay? So that's the solution in geometric form. But let's get back to the task of verifying that our solution is correct. Okay? All right, good. So we have x is equal to -1 plus t. So let's substitute that into equation 1, -1 plus t. Then we have 2 times y, which is 2 minus 2t. And then we have 3 times z, which is 3 times t. Now, hopefully that's all equal to 3, right? So let's see, what do we get? What do we have as far as numbers and as far as t's? As far as numbers, we have -1 plus 4. That's looking good. As far as t values, we have t minus 4t plus 3t. Okay? So you can see that the t's are going to cancel because t minus 4t is -3t plus 3t is 0 t's. And -1 plus 4, of course, on the left-hand side is 3. So we see that our solution checks with equation 1. So let's see what we have for equation 2. Well, we have 4 times the quantity -1 plus t. Then we have 5 times the quantity 2 minus 2t. And then we have 6 times t. And that all is to be equal to 6. So let's see what we have in terms of numbers. In terms of numbers, we have 4 times -1, which is -4, and 5 times 2, which is 10. That's looking good, right? In terms of t's, we have 4 times t, which is 4t, and 5 times -2t, which is -10t, and then plus 6t. So is all this equal to 6? Sure, because 6t plus 4t is 10t, minus 10t is 0t, and of course 10 minus 4 is 6. And so we see that 6 is equal to 6. Good, so equation 2 checks. Now let's check equation 3. So for equation 3, we have 7 times -1 plus t, plus 8 times 2 minus 2t, plus 9 times t. And all that's supposed to equal 9. Well, what do we have? In terms of numbers, we have -7, okay, and then 8 times 2 is 16, all right, which is equal to 9, so that's great. And then we have 7t, right, minus 16t plus 9t equals 9. And do the t's cancel? Sure they do, because 7t minus 16t is -9t, plus 9t is 0, and as I said, 16 minus 7 is 9, so we have 9 is equal to 9, and equation 3 checks, which is great. So this linear system has infinitely many solutions, different from previous linear systems that I did for which the solution is unique. Okay, we call this a one-parameter family of solutions. Okay.